23,000 feet above the English Channel on the night of the 17th of August, 1943. Oberleutnant Klaus Hartmann feels his Junkers Ju-88 shudder. The vibration travels through the control column into his hands. His radio operator shouts something incomprehensible through the intercom, the words drowned by a shrieking electronic howl that tears through their headsets. Hartmann banks hard to starboard, scanning the darkness for night fighters, but sees nothing. No tracer fire, no searchlight beams, just the suffocating roar of static, and beneath it, something else. A pulsing, mechanical scream that seems to come from everywhere and nowhere at once. His instrument panel flickers. The compass needle spins uselessly. He cannot hear his crew. He cannot hear his engines. For 30 seconds that stretch into eternity, Hartmann is alone in the dark, blind and deaf, whilst enemy bombers stream past him toward the Ruhr Valley. When the howling finally stops, he has lost his formation, his bearings, and any chance of intercepting the raid. This is not the result of British bullets or bombs. This is something entirely new. A weapon that exists nowhere on his aircraft recognition charts, that fires no shells and leaves no wreckage. A device that reaches across empty sky and rewrites the rules of aerial warfare by making the very air itself hostile to German electronics. By war's end, this invisible weapon would be feared more than fighters, more than flak, more than the creeping certainty of mathematics that said no bomber crew could survive their tour. The British had learned to weaponize the electromagnetic spectrum. The problem facing RAF Bomber Command in 1942 was brutally simple. German night fighters were massacring British bombers. The Luftwaffe's Kammhuber line, a defensive network stretching from Denmark to central France, had transformed night bombing from a dangerous mission into something approaching suicide. Each raid was hemorrhaging aircraft at unsustainable rates. In a single week during November 1941, Bomber Command lost 73 aircraft. Not to flak, not to mechanical failure. To night fighters guided by an increasingly sophisticated electronic web. The Germans had developed a deadly coordination of ground radar, radio communication, and airborne interception radar that allowed their fighters to find bombers in complete darkness. The Würzburg radar could track RAF bombers from 70 kilometers away. Ground controllers would vector Messerschmitt Bf-100s and Junkers Ju-88s into position. Then the fighter's own Liechtenstein airborne radar would guide them through the final approach. The system was murderously effective. A bomber crew's first indication they had been found was usually a stream of cannon fire tearing through their fuselage from behind and below. By mid-1942, Bomber Command was losing roughly 5% of aircraft on every raid. The mathematics were unforgiving. Standard operational tours required 30 missions. With a 5% loss rate, only 22% of air crews would survive their tour. Something had to break this deadly efficiency. Traditional countermeasures had proven inadequate. Flying higher made bombers easier to track on radar. Flying lower brought them into range of flak. Tighter formations made better radar targets. Looser formations left bombers isolated. The fundamental problem was that the Luftwaffe could see through darkness and Bomber Command could not hide. The solution emerged not from bomber specialists, but from a telecommunications research establishment tucked away in the Dorset countryside. The Telecommunications Research Establishment at Worth-Matravers, relocated from Swanage after concerns about German raids, housed some of Britain's most brilliant scientific minds. Among them was Dr. Robert Cockburn, who had spent months studying captured German radar equipment and prisoner interrogations. Cockburn realized something crucial. The German radar and radio systems all operated on specific frequencies. If those frequencies could be overwhelmed with noise, the entire defensive network would collapse. The concept was elegantly simple. Broadcast enough electromagnetic interference on the right frequencies, and German radar screens would show nothing but blizzards of false returns. radio communications would dissolve into static. Airborne intercept radar would be useless. The principle was similar to shouting in a quiet room. If someone shouts loud enough, all other conversation becomes impossible. The device itself, codenamed Mandrel, was essentially a powerful radio transmitter tuned to broadcast noise across the frequency bands used by Würzburg radar. Early prototypes were tested in April 1942. A Mandrel set consisted of a transmitter producing roughly 600 watts of radio frequency power, an array of aerials, and the power supply to run it. The entire assembly weighed approximately 130 kilograms. Crucially, Mandrel could be fitted into a bomber's fuselage without removing any weapons or crew positions. The device worked by generating what engineers called noise jamming. Unlike later, more sophisticated systems that created false targets, Mandrel simply flooded German radar receivers with meaningless signals. Imagine trying to listen to a whispered conversation while someone runs a chainsaw next to your ear. The whisper doesn't disappear, but it becomes functionally non-existent. Manufacturing took place at several locations across Britain, with final assembly concentrated at facilities in Malvern. Production numbers remain partially classified, but estimates suggest roughly 1,200 Mandrel sets were built between 1942 and 1944. Each set cost approximately £800, roughly equivalent to a decent motor car at the time. The transmitter used valve technology, essentially scaled-up versions of the components found in commercial radio sets, but pushed to their absolute limits of power output. Mandrel first saw operational use during a raid on Hamburg on the night of 30 January 1943. 8 Sterling bombers from No. 199 Squadron carried the equipment, flying in a screen ahead of the main bomber stream. The results were immediate and startling. German controllers reported that their radar screens had suddenly filled with interference. Track plots became impossible. The careful choreography of interception vectors collapsed into confusion. That night, Bomber Command lost fewer aircraft than on any comparable raid in months. But Mandrel was only the beginning. Scientists at TRE quickly developed an even more devastating variant called Window, though this operated on different principles. More significant was the development of Airborne Grocer, a system that jammed the Liechtenstein Airborne Intercept Radar, fitted to German night fighters. This device was smaller, lighter, and could be operated by the bomber's wireless operator. When a German night fighter switched on its Liechtenstein radar to make the final approach, the bomber's Airborne Grocer would detect the signal and immediately blast back overwhelming interference. The fighter pilot would suddenly lose his radar picture entirely, usually at the worst possible moment. The psychological impact on German aircrew was profound and immediate. Night fighting had always been technically demanding, but the Liechtenstein radar had given pilots confidence. They could hunt in the dark with electronic certainty. Now that certainty evaporated, pilots reported their equipment failing without explanation. Ground controllers lost contact with their fighters at critical moments. The carefully constructed system of electronic warfare that had cost the RAF so dearly began to crumble. If you're finding this interesting, a quick subscribe helps more than you know. These technical histories take considerable research to get right, and your support makes them possible. The Germans were not standing still. The Luftwaffe recognized immediately that they were facing electronic countermeasures and responded with characteristic engineering thoroughness. By late 1943, they had developed new radar sets operating on different frequencies. The Liechtenstein SN2 operated at lower frequencies where British jamming was initially less effective. German radio communications shifted to different wave bands. New procedures were implemented. Ground controllers began using visual observation posts to supplement radar. The Luftwaffe also developed their own jamming equipment, though they deployed it primarily against British ground radar rather than airborne systems. Their Kettenhunt transmitters could blind British early warning radar, making it harder to scramble fighters against incoming German raids. In terms of raw technical capability, German radar technology was often more sophisticated. Their Würzburg system was arguably more accurate than equivalent British sets. However, the British had one crucial advantage. They innovated faster. When the Germans changed frequencies, British scientists would capture new equipment, analyze it, and have countermeasures deployed within weeks. This wasn't superior technology. It was superior operational science. The TRE team had established a cycle of capture, analysis, development, and deployment that the Germans could not match. American forces developed parallel systems, though generally with more emphasis on power and less on elegance. American jamming pods produced significantly more power than British equivalents, but were correspondingly larger and heavier. The USAF's approach reflected different operational needs. Their daylight bombing raids faced different threats, primarily German fighter communications rather than radar. British systems were optimized for the specific electronic environment of night bombing over Europe. This gave them an edge in that particular domain that American equipment, however powerful, could not replicate without modification. The historical impact of electronic warfare equipment, like Mandrel and Airborne Grocer, is difficult to quantify precisely, but certain facts are undeniable. RAF bomber losses decreased markedly after these systems entered service. In the first quarter of 1943, before widespread jamming deployment, Bomber Command lost an average of 4.7% of aircraft per raid. By the final quarter of 1943, this had fallen to 3.3%. That difference, roughly 30% reduction in losses, translated to hundreds of aircraft and thousands of aircrew who survived when they otherwise would not have. The Germans themselves acknowledged the impact. Luftwaffe night fighter ace Heinz Wolfgang Schnaufer described the sudden appearance of jamming as creating electronic fog that transformed night fighting from a technical exercise into desperate guesswork. Post-war interviews with German radar operators consistently mention the period from mid-1943 onward as one of increasing frustration and diminishing effectiveness. However, attributing specific outcomes to electronic warfare remains problematic. The same period saw improvements in British bomber tactics, deployment of long-range fighter escorts, and the gradual attrition of experienced German pilots. Window, the metallic chaff that created false radar returns, probably had more immediate tactical impact than active jamming. What electronic warfare equipment like Mandrel demonstrably achieved was forcing the Germans into a costly technological arms race they could not win. Every frequency change, every new radar set, every modification to fighter equipment consumed resources Germany could not spare. The influence on post-war military thinking was profound. Every modern air force now operates on the assumption that electronic warfare is as fundamental as ammunition. The concept that the electromagnetic spectrum is a battle space, not merely a communication medium, traces directly back to these pioneering systems. Original Mandrel equipment is extraordinarily rare. The RAF Museum at Hendon holds one partial set, though it is not usually on public display. Most were simply scrapped after the war, the valve technology having been superseded. Ironically, the thing that made German pilots panic has been largely forgotten by history, overshadowed by more photogenic weapons. 23,000 feet above the English Channel, on that August night in 1943, Oberleutnant Klaus Hartmann eventually regained control of his aircraft. He would file a technical fault report that his commanding officer would read with grim recognition. Similar reports were accumulating. Equipment failures, unexplained interference, radar screens whiting out at crucial moments. The invisible had become weaponized, and there was no armor that could stop it, no evasive maneuver that could avoid it. This was warfare conducted in a domain that did not exist on any map, fought with equipment that fired nothing and hit everything within range. The British had not merely invented a new weapon, they had invented a new category of weapon. Before Mandrel and its descendants, electronic equipment was infrastructure, vulnerable but passive. After these devices entered service, the electromagnetic spectrum became contested territory. Every radar pulse was now a potential vulnerability. Every radio transmission could be exploited. The air itself, invisible and intangible, had become hostile in ways that no pre-war military planner could have imagined. By the time the war ended, electronic warfare had expanded from a desperate expedient to a fundamental component of air operations. The device that made German pilots panic mid-air was not the last word in electronic warfare. It was the first word. Everything that followed, from Vietnam-era wild weasel missions to modern stealth technology, traces its lineage back to those 130-kilogram boxes of valves and wire, humming away in the bellies of British bombers, turning the night sky into an ocean of meaningless noise through which German fighters groped uselessly whilst RAF bombers pressed on toward their targets. The howl in Klaus Hartmann's headset was the sound of the future. He just did not know it yet.